So we're going to continue looking at the general linear models. We're going to spend a little bit more time now thinking about interpreting things, in particular how we can, like we've just done with centering the predictor variable, how that not only helps our fit, as we talked about, but also how it will help potentially aid in interpretation and a few other things we can do. And we can kind of consider this as a precursor to thinking explicitly about how we want to measure effect sizes so that they're most interpretable. And if you remember, the last thing we did is we did for the regression of sex comb teeth onto the tarsus length, we centered tarsus length. And this top plot here, again, is just that same plot with all the spots just being the observed variables. And so that our intercept now is at the mean of tarsus length. So that means that if you just look at the mean of centered tarsus, it's 0, but the intercept itself represents now the mean for tarsus, and that we're fitting a model within the range of our data. So we're not extrapolating well outside of the range of data, which dealt with a couple of issues as we saw. And as we see in this lower plot, in parameter space, we got rid of virtually all of the covariation between the parameter estimates. And we can use, again, the cov2core function for the regression model, and we see here that the covariant or the correlation between the parameter estimates is effectively 0. Negative 5.4 times 10 to the negative 16 is close enough to 0 for me anyways. All right, but what we want to do now is sort of think about interpreting that. So let's just clear the that. And we'll blow the R window open a bit. So the slope is identical to what we have before, and I'll just demonstrate that. We just go first regression, which is regression.1. And so that's 26.9. And we see that we have exactly that same estimate here, 26.91. And in fact, if we look at the standard errors, they'll be identical. You will notice, however, of course, that the intercept is not identical, nor is the standard error. And we've already discussed why. Part of it is that the pivoting issue and estimating well outside the range, those would both increase the standard error well outside the range, which it really, in terms of our estimation, really should be. And now our intercept, or again, we're estimating it at the value of 0 for tarsus, or new tarsus of centered tarsus, is 11.13. So we're saying when tarsus is at its mean level, or centered tarsus is at 0, our expected number of sex comb teeth is 11.13. So essentially at the mean. And our slope is the same. So it does make a lot more sense. Unlike before, where our estimate for the intercept was 6, for when a tarsus actually was a true 0, here it's when tarsus is whatever. We can calculate the mean of data tarsus. So when tarsus takes the value of about 0.187, we expect the number of sex comb teeth to be about 11.13. And that makes much more sense. And you'll see the rest of our statistics, residual standard error is still 1.55. R squared hasn't changed. It's still, we count for about 8.5%. The F statistic. So the only thing that changes is really the intercept, and it makes it much more interpretable, which is good. Let's shrink this back down. Okay, we're going to ignore the simulation again. For people who care, there's another, this is part of the, probably the CAR package, or the ARM package rather. There's the Gelman and Hill likes to, instead of having the big summary or just the small coefficient display, it has a slightly extended version of coefficient, where it has just the coefficient estimates and the standard errors associated with those estimates. And here's actually sort of useful. You can see that for the centered data, our coefficient is 11.13 with a standard error of 0.04. When we're estimating the intercept for tarsus itself, we're not centering, so we're extrapolating out, we have a coefficient of 6, and our standard error is what, almost 7 times as large. So it's much, much larger. The ARM package, which is the one associated with the Gelman and Hill, also has some reasonably useful plotting. I would say that they're reasonably useful. They're good for sort of quick plots to actually make them look pretty. They're a little bit more difficult, but essentially they give you the estimates. You specify a couple of arguments, so you can set the flag equal to true for intercept if you want to plot the intercept, whether you want it to be vertical or horizontal, and then other things like y limit. And it'll plot here the intercept and the estimate for our slope. You can't see it because the standard error is so slow, but there is a standard error associated here around the intercept, which is very small. For Tarsus, for the slope, you can see the thicker black lines here, one standard error, the thinner black lines are two standard errors, which of course is approximately the confidence intervals. And you can change that in the arguments there. And like I said, by centering the covariate, by centering Tarsus, we can now interpret the intercept as the expected number of sex-comb teeth at the mean value of Tarsus length. Okay, one thing to keep in mind though is that estimated slope, 26.9. So what's this telling us, right? What is the slope of 26.9 out here telling us? Well, it's saying that for every unit increase by 1, of Tarsus, and whatever unit it's measured in, millimeters, centimeters, whatever, the number of sex-comb teeth is predicted to increase by 26.9. Okay, well that seems reasonably sensible until we actually look at the range of values that Tarsus can take. So we're going to look at the quantile as one way of doing that. And our quantiles show us that our observed values for Tarsus go from about 0.1 to 0.258. So that means our range is really about 0.15 units. Whatever units is measured in is probably millimeters, or 0.10 to 0.258. So a change of unit length, i.e. from 0.1 to 1.1, goes far outside the biologically plausible range. So that slope, 26.9, is clearly much bigger. A unit change is much more than we'll ever see. So that slope is really, it exaggerates what biologically we really should be interpreting. So one of the things to do, and we'll spend some time thinking about this in class as well, though we'll go through a quick activity here, is how do we aid in interpreting the coefficients in the model? And there's a couple of very straightforward things we can do. So the first thing we can do is we can just interpret very carefully, right? We can say, well, instead of saying let's think about what would happen if we increase by unit length, we can say what happens to sex-comb teeth if we increase Tarsus by 1/10 of a unit length, of 0.1. So in that case, instead of predicting an increase of 26.9 sex-comb teeth per unit length of Tarsus, we're saying per 0.1 unit, which is biologically plausible, we expect an increase of 2.69 sex-comb teeth, which is much more reasonable and easier to explain. So we're basically saying if we go from the individuals with the smallest tarsi to the largest tarsi, we'd expect, based on this model, them to have the ones with the largest tarsi to have on average about 2.7 additional sex-comb teeth. And again, we can look at this sort of thinking about the range. So the range is 0.1 to 0.258. And one thing we can do is just multiply that range by 26.9, and that suggests at the largest, for our largest range of variation, we'd expect an increase of about 4 sex-comb teeth. And that gives us a sensible reason. And we can think about that in terms of something like, well, how much variation do we observe? Our standard deviation for sex-comb teeth is 1.62. So if we double that, which is that 3.2 and change, 3.3, that's 95% of observations we expect to fall within that range. So of the mean. So that would say if our mean for DLL.beta is 11.13, we really expect them to be somewhere between somewhere around 9 to somewhere around 14 is where we expect to observe it. And if you think about that, if that's sort of the range of our observations, an increase of 3 or 4 sex-comb teeth in terms of Tarsus, that's pretty substantial. So that actually gives us some indication of the influence of it. It does seem to have an effect. We know from the previous plot, it's not accounting for a lot of the variation, but between what we've seen from the confidence intervals and the plots, it says there's probably something there. And as written here, it's approximately 2 times greater than the standard deviation for sex-comb teeth. So, it's probably biologically important. At least in my mind, this would suggest that there's something biologically interesting here. And of course, there's uncertainty with our point estimates here, so it's worth doing this for confidence, or posteriors if we're doing Bayesian. So for instance, we can essentially use the confidence intervals for the slope, which go from 23 to 30, and we're going to multiply it by 0.15, which is the range of values, And so we're saying that the increase over the whole range of values for tarsus is somewhere between an increase of 3.5 to 4.5 sex comb teeth, essentially, or 3.45 to 4.62. It doesn't really change our biological interpretation of tarsus length as a covariate, but it gives us some indication of the uncertainty associated with that. Okay, so that's one way we can go about doing it. Are there others? Of course there are. So one clear and perhaps more straightforward thing we can do is recode tarsus length to say micrometers instead of millimeters. And so here we're just going to multiply the centered tarsus length. We still want to keep it centered. We're just going to recode it because, of course, 0 micrometers is as meaningless as 0 millimeters in terms of the length of a tarsus. So we'll just recode that. We can refit the model. Of course, I think you probably can imagine what's going to happen here. It's not going to really change our interpretation. Our intercept is the same. The only thing that changes is where the decimal place is for the slope now. So instead of it being 26.9, it's 0.0269. And that's basically saying for every micrometer increase in tarsus length, we expect a increase of 0.027 sex comb teeth. And then we can ask, again, with the range in micrometers being, because of course it's centered from negative 81 to 70, but over a range of essentially 150 micrometers. What do we expect? And we multiply 150 micrometers by our slope, and we would actually get the same essential results as we saw above from just thinking about it in terms of the units. So it doesn't change anything other than the estimate for its slope and centered error, and really just 1,000 times smaller. But it can make it easier to interpret. Essentially, we can think about unit increases where the unit is a micrometer. So that's perhaps one way of doing it. Either of those is fine. And again, we just sort of think about what makes it biologically easy for us to interpret. Now, one of the last things I'll talk about for this is data normalization. And this is a very important but also contentious issue in both statistics and in biology. So one of the common things we do in biological science is what's often done is we will standardize our variables. We'll standardize our predictor variables. So in studies of natural selection in the field, when you're estimating phenotypic selection gradients, as many of you learned about, you actually standardize all of your predictor variables. You look at relative fitness, which is just scaled by the mean of fitness, but for these you will center, like we've done before, but then you also divide by the standard deviation for that predictor. So you, like I say here, you normalize the data by dividing all values of, say, tarsus by the standard deviation of tarsus. And if you do it on center data, it's called unit standardized data. You can also use the scale function to do this. You just have to specify center equals true and scale equals true, which is actually the default, so you don't have to do it. The issue here, though, is if you normalize, the reason we do this, before I say the issue, the reason we do this is this allows us to compare all of the different variables. So if we had lots of different predictor variables, and say some in units of concentration, some in units of length, and whatever, how do we compare those? And this allows us to put them all more or less on a standardized scale, unitless scale, and that's very convenient. And that's, in fact, exactly why it's done for phenotypic selection analysis. However, if you do this, you're no longer thinking in units of the measured variable, but in changes of the units and standard deviations. So a unit change is a standard deviation, is now your unit. So this can be very useful for covariates which are difficult to compare, nutrient concentrations and water temperature, but it also can make interpretation take you a little longer. I should also say that part of the reason it's contentious is because, despite its utility, there's a lot of arguments about when that's a use. Standardizing or scaling by the standard deviation is the way to go. One of the other alternatives, which is broadly used, is a mean scaling. So you essentially divide by the mean of that variable. So you center by the mean and divide by the mean. And so it's in units of changes at a mean level. And people like David Houle have advocated this quite strongly, in particular for measures of phenotypic selection and a few other things. So let's take a look at this. We're going to scale this, and we'll just use the scale function here. So we're just saying tarsus.std for standardize as numeric. I'm not sure if that's actually necessary anymore to do the as numeric, but just scaling it. And like I said, the default is for it to both center and to standardize by or scale by the standard deviation. So we run that, and then we'll run regression.4 is the name of this one. And this will actually change the estimates here, and so this is important to take a look at. So here is the summary. So, all right, there we go. You'll see that the estimate, in this case of the intercept, that's not going to change. But our slope, instead of it being 26.9 or 0.0269 or whatever, it's quite different. It's not some just scaling, because it's no longer in units of Tarsus length. It's now in units of standard deviation of Tarsus length. So what this is saying, for every unit change, standard deviation change in Tarsus length, we increase sexcomb teeth by 0.48. So we expect plus or minus 2 standard deviations to include 95% of all our observations for Tarsus lengths. So if that's the case, we can essentially think, well, that's going to be 4 for 2 less and 2 greater times that 0.48. And so we expect essentially about 1.92 increase, which is giving us a slightly different answer than what we saw before, and we should think about it. So this is giving us a slightly different answer. You'll notice that there are some things that are essentially the same. Our residual standard error really hasn't changed very much, but it can. Multiple R squared really hasn't changed very much either here. So this has scaled it. It does change, however, the interpretation, and one wants to be careful. When you have lots of covariates that are in different units, though, it is often worth considering either doing scaling by the mean or by the standard deviation, and it's worth considering. And this sort of just repeats what I've said. So a standard deviation unit is 0.01 millimeters of Tarsus length, and like I said, for the slope, it's now interpreted as saying for each increase by 1 standard deviation in Tarsus length, or 0.18 millimeters of Tarsus length, sexcomb teeth increases by 0.48. And we can plot this and put our lines on it just like before. Here are just our confidence intervals. And let's grab the plot here, which is down here. It's going to look pretty similar, not surprisingly, but this is now, you'll notice that the units here on the x-axis are quite different. 0, -4 to 4. Quite a different set of units. Okay, and similarly, if we do the coefficient plot, well, I clearly didn't put the intercept on here, but it gives us a slightly different plot. Okay, and we will end there for this tutorial.